Hi guys, so welcome again. In the last video of strength of materials, we have learned how to calculate your strength for any plane when your stress are applied like this, or in the both mutually perpendicular plane your stress is applied, and you have learned how to calculate the normal stress in any plane like this. Okay, along with normal stress you have also learned how to calculate the shear stress, and beside application of mathematics formula you have also learned how to apply your graphical method by the stress circle method. Okay, and today's lesson we will learn what is your principal stress and what is your principal plane. Okay, so principal stress versus your principal plane, this is the topic of today's lesson. Let's start. So in this case, let's say the stress was sigma x and this was sigma y, and in your stress circle let's draw a better stress circle. Here this is the axis, and let's say this was your circle. Okay, and this value was your sigma x and this was your sigma y, and our assumption was sigma x is greater than your sigma y. So can you tell me what is the shear stress here? Here your shear stress is 0, and here is also shear stress is your 0. In this figure also you can see here that in this vertical plane here is only normal stress, there is no shear stress. Similarly in this plane also here is only normal stress, and this is sigma y, there is also no shear stress. So from here we can say where your shear stress is 0, that stress, that normal stress is known as your principal stress. Clear? So in this case what is the principal stress? Sigma x and sigma y. Okay, so the maximum principal stress can be denoted by sigma 1, that is your sigma x, and minimum is sigma 2, that is your sigma y, and the plane corresponding to this sigma stress, or in the plane where your shear stress is 0, is known as your principal plane. Okay, so what is the principal here, principal plane here? This is the principal plane, this one, and also this one is your principal plane. So this is the case where your only normal stresses are acting in both the perpendicular faces. Okay, but in real life it is possible. Let's say this is your body and your normal stresses is acting like this. This is sigma x, and in this space this is sigma y. Okay, both are tensile in nature, and let's say sigma x is greater than your sigma y. Okay, along with this normal stress there is also acting your shear stress, and it is, let's say this is acting like this. Okay, this is one shear stress, and in this phase this is another shear stress. Okay, so in this case obviously this plane is not your principal plane because here shear stress is acting. Also this plane is not your principal plane because here is also shear stress is acting. So let's find what is the principal stresses and what is the principal plane, or where this principal plane belongs. Okay, maybe here or maybe here somewhere. Okay, so let's start. And to find these principal stresses and also the principal plane, we'll use the graphical method. Okay, you have already learned how to draw your stress circle. In the last two videos I have discussed detail how to draw this stress circle. Okay, now we will use this stress circle method or graphical method to find these principal stresses along with the principal plane. Okay, so let's start. This is your body and the stress are acting like this. This is sigma x, everyone is tensile in nature. Okay, this is sigma y, this is sigma y, and sigma x is greater than sigma y, And what is the value of shear stress? Your shear stress is acting, let's say, like this here. This one, this is positive, okay. For x direction it is positive, and in y direction it is negative. Why? Because this is creating anti-clockwise motion. So for y direction this is negative, okay. So let's draw the your stress circle. This is the axis system, and this is your circle. So before drawing the circle, let's first point out the point or the coordinate for x direction. This is for normal stress, this is for your shear stress, okay. This is positive, negative, this is positive, and this is negative, okay. So first plot sigma x. Let's say this is somewhere here, this is sigma x, and corresponding to sigma x, what is the shear stress? This is tau, and it is positive. So you have to plot in the direction of positive axis, okay. So go up to tau, let's say here, and this is your tau. So this is our first point, clear. Now come to second point, sigma y. For this plane the normal stress is sigma y. It is tensile in nature, so positive from origin. So let's say this is sigma y. And what is the shear stress corresponding to this plane? It is negative, but magnitude is same, that is tau, okay. So plot it, let's say it is somewhere here. Let's define this point as A, this point as B, this point as D, and this one, let's say D dash, okay. So you have plotted all the coordinate. Now connect D and D dash, okay. Let's connect it. So connect D dash and D, okay. It will intersect somewhere here. Let's name it AB, your C, okay. What is the coordinate of C? Simply average of coordinate A and B, that is your sigma. This was your sigma x, this was your sigma y, and coordinate of C is sigma x plus sigma y by 2, okay. So what is our next step? Next step is draw the stress circle, and to draw the stress circle we use our D dash as diameter and C as your center, okay. So draw it. This is the coordinate, and you have already defined all the point, that is your A, sorry, this is B, B, C, this is your D, okay. Sorry, this is your A, and this was your D, this was your D dash. We have connected D dash to get center C. Now we have to draw our circle. So circle is something like, looks like this, okay. So let me draw it correctly. Now the circle looks great, okay. This is the center. And what is the principal stress? Simply the principal stress is your principal stress is corresponding to your plane where your shear stress is 0. So you can see here clearly, here shear stress is 0 and here shear stress is 0. So obviously the normal stress here sigma 1 denotes your first principal stress, and this normal stress here sigma 2 denotes your second principal stress, okay. So let's find the magnitude of all these principal stress. What is the coordinate of each point? A was your sigma x. Let's change the color for your better understand. Sigma x, this was your sigma, B was for sigma y, and this was tau, this was also tau, and C was sigma x plus sigma y by 2. So if we have to find this, let's say this is E point, this point is E, this point is your F. Okay, so what is sigma 1? Sigma 1 is simply, this is origin O, so OC plus CE. So OC plus CE. Now what is CE? CE is simply the radius or CD. Clear? So what is the value of CD? CD is square root of, from Pythagoras theorem, AC square plus your AD square. What is AC? A is your, sorry, OA. OA was sigma x and OC was sigma x plus sigma y by 2. So what is this? CA. Simply we can subtract OC from OA. Okay, so CA is coming as your OA minus OC, or sigma x minus sigma x plus y, sigma y by 2, that is coming as your sigma x minus sigma y by 2. So you have got CA or AC. Okay, so put here AC is your sigma x minus sigma y by 2 whole square plus AD. What is the value of AD? AD is your tau, that is tau square. So you have got CD. Okay, so CD is your CE. Now sigma 1 is coming as OC. OC is your, what is OC? OC is your this one, sigma x plus sigma y by 2 plus CE or CD is plus sigma x minus sigma y by 2 whole square plus tau square. So you have got your first principal stress or maximum principal stress. Now we have to find the second one, or this one. This is your sigma 2, and sigma 2 is your OF. OF is your OC minus CF. Again, CF is the diameter or radius, or CD. You have got the value of CD. And what is OC? It is known to you. OC is this one, or the coordinate of C, that is your sigma x plus sigma y by 2. So sigma 2 is coming as your sigma x plus sigma y by 2 minus CF or CD, that is your square root of sigma x minus sigma y by 2 whole square y plus tau square. So you have got both the principal stresses. Clear? Now this is time to find the principal plane. So before that, what is the maximum shear stress for this type of stresses? What is the maximum shear stress? Simply from this circle you can see the maximum shear stress is denoted by this point, and to reach there we can simply draw the perpendicular from center to this point, and this is nothing but your radius of the circle, and this circle is known as Mohr circle. Okay, so what is the radius? Radius is CD. Okay, and this is denoted by this formula. So what is the maximum tau or tau max? That is your sigma x minus sigma y by 2 whole square plus tau square. If you simplify, or if you retain these two formula like this, sigma 1 minus sigma 2 by 2, then this gives you the same formula. So tau max can be written like this also. Once you find this sigma 1 and sigma 2, or the two principal stresses, you can simply find out what is the maximum shear stress acting for this type of stress situation. Clear? So now it's time for calculating the principal plane. Again, recap the previous cases where simply you have applied a single tensile stress, and here the plane was 5 degree away from the actual normal plane, or this one. Okay, and to find the normal stresses you have used already the graphical method. Okay, so what was the cases there? This was sigma x, and to find the stresses on this plane you have rotate this radius anti-clockwise for 2 phi angle. Okay, and then corresponding to this point you have find this normal stress as well as this shear stress. So here also in this circle, let's see, here you can see here that this point, okay, this point is somehow denote your actual plane where the both normal stress as well as your shear stress is acting. Okay, so this was your actual plane and this represent this vertical plane. Okay, now in this plane this is the principal stress and this is, let's say, 2 phi degree away. Okay, but it is measured clockwise. Okay, so if you know the value of 2 phi, then you can plot the principal plane. Okay, so let's say we know the value of 2 phi. So to plot the principal plane we will simply, let's say this was your actual body. Okay, and here we have seen that your 2 phi angle has been measured clockwise. Okay, to reach this principal plane. Clear? So here is also just rotate this clockwise for 5 degree and you are getting this plane. So when your stress is applied like this, these are the shear stress, these are shear stress. Okay, so for that the principal plane is somewhere here where your shear stress is here, your shear stress is 0, only normal stress is acting. Also similarly for this one, this principal plane, you have to rotate or you have to go more pi by 2 degree away, or in case of graphical representation you have to go for pi degree away, pi radian. Okay, or 180 degree. So here we have to rotate it again. We have already rotated it for phi in clockwise direction. Again we have to rotate it for pi by 2, because in graph it was 180 degree, in real case it is 90 degree. So again rotate 90 degree clockwise, you are getting this one. So this is another principal plane where you shear stress is 0 and principal stress is sigma 2. Here it was sigma 1. Clear? So if you want to know the value of phi, you can plot your principal plane like this. So what is the value of phi? Simply, this has become quite clumsy, still let's draw it clearly. So this is our coordinate system, this was our circle, let's say this circle. Okay, and this was center C, this was A, this was B, this was E, this was F, this was D. Okay, and this was your D test, like that. So what is 2 phi? We have measured clockwise 2 phi. So tan 2 phi is equal to dA by your CA, no doubt in that. And you know dA is your tau, and CA you have already find out the value. What is CA? Let's check. CA is coming as your this one, this is CA, this is sigma x minus sigma y by 2. Okay, so sigma x minus sigma y by 2. So your 2 phi is coming as tan inverse 2 tau by sigma x minus sigma y. So you have also find out the location of the principal plane. Now you can simply rotate this plane for phi degree in actual figure here. Okay, simply rotate it clockwise manner. You will get this one for sigma 1, and again rotate this for another pi by 2. You will get another principal plane. Okay, now here is a problem related to sign. In some books you can see in this formula here is a negative sign. Okay, don't confuse with that sign. Simply when you are taking negative sign, you will get a phi value. Let's say this is 2 phi dashed, and in that case you have to rotate your plane, actual plane, in anti-clockwise manner. Okay, so here this is your sigma 1, and again for phi by 2 anti-clockwise, this is your sigma 2. Clear? So don't be confused with your minus sign. When you take clockwise measurement, you have to simply rotate it clockwise. If you take anti-clockwise measurement, you have to put minus sign, and in real case you have to rotate your plane in anti-clockwise manner. That's all. Okay.